So welcome back to the continuation part of this video. And in this video, I'll be doing the physics and meshing, and if possible, we'll compute the work. Previously, we did build our geometry and add parameters. We also defined some definitions and variables in the work. So if, like I said in the previous videos, if there was any part that I didn't understand, you could just write it down in the comment section and I'll do well to address that. Also, if you need one-on-one assistance with your work, please do well to subscribe to our membership group as a subscriber, and I'll do well to provide you with assistance. Okay, so let's start this work. In this work, we will start with our secondary current distribution. And remember, we added secondary current distribution, added Darcy's law, and all that. So go to secondary current distribution. Let's add an electrode. And for the electrode, we'll select domain 1 and 3. And under the electrode settings, we'll look for this electrical conductivity, which will make a user-defined. And we'll name this as copper_M. Yes, sorry. Let's go to electrolyte 1. Similarly, for the electrolyte conductivity, it should be a user-defined electrolyte. And this will be copper_M. Then we'll add go to boundaries. And let's look for an electric ground. Electric ground would be at boundary 8 only. Look for boundaries and look for the electrode potential. Electric potential, sorry. This will be at boundary 17. And where we have the electric potential, so at the file electric potential value, have to change this to potential of the cell. This already define the parameters. And we add an internal electrode surface. For the boundary selection, we'll be using the anode electrode. We'll also add electrode reaction as well. 。 we look for the electrode reaction, should be here. So under the electrode reaction one, where we have the over here. Let's make here the kinetic expression will be a user defined so that the local current density can be defined as I underscore A. Okay. We have this. So we locate the default model input. And under general, we should locate the temperature K here. So when you click over here, this side, you're going to type T. So now let's go back to our secondary current distribution under physics. We have boundaries. And let's add the second internal electrode surface. Okay, the boundary selection, and here will be a cathode electrode. The cathode electrode. Expand the electrode, internal electrode surface, you'll find the electrode reaction. And then under the setting of the electrode reaction, okay, the electrode kinetics, you make a user defined, and under the local current density, you make a I. So see, you have to set the initial values. Domains, and we'll have initial values. That will be for domain 3. And for the initial values here, under the electric potential, we put this value here, this expression here. So we are done with the secondary current distribution. We move to Dark's law, sorry. Under the domain selection, we'll do it manual. And let's delete domain 2 out of it. So it's just, you're selecting just 1 and 3. And we locate the physical model, and we should have this reference pressure. Should be 0. And the dark store, we have fluid and matrix properties. And over here, we try to locate the fluid properties. And under the row should be user defined. We make a row mix. And we locate the matrix properties. We'll make a user defined, so you can put an expression there. Look at this expression. Locate the fluid properties. So the dynamic viscosity should be user defined. That'll be eta. Matrix properties, user defined. U1. Go to initial values 1. Under the pressure, put this expression there. Add another pressure from this physics. And here, we'll name this expression P underscore E underscore E. We add another pressure. This will be at boundary 22 only. And this expression will put P, let's go C. We add another pressure. This will be boundaries 4 and 21 only. This expression will be P, let's go reference. So the next is to add electrode surface coupling, used to create a boundary condition for the flow. Let's go back. Yeah. We said the selection here is empty because we did not select the boundary. What's the boundary 1? So for pressure 1 is boundary 1, pressure 2 is 22, pressure 3 is 4 and 21. So Under the boundaries, we locate the electrode surface coupling. The boundary selection be the anode species. We're going to add and molar mass for one being M, 2, MH 20. Expand this electrode surface coupling. Then under the reaction coefficients, 1, locate the input. You have to locate the local current density. We'll be using this. Under the stoichiometric coefficients, let's put this species there. Coefficients there. 2 times drag. Let's go back to physics and we have the boundaries. We add a second electro surface coupling. But here it will be for only boundary 13. Add more species to make it 3. So here will be M02. H2 MN2. And under the reaction coefficients 1, local current density using the second one, this local current density. Number of species will be 4. That will be -1. That will be 2 plus 1 times 4. Now we go to transport of concentrated species. We want to rename this to transport of concentrated species. We want to make a transport of this anode. And under anode, you select the anode GDL. From this diffusion model, I want to choose Maxwell Stefan. And for the species, you want to choose WH2OA. Let's go to transport properties. Under the density section, rho is user defined to give us a rho mix. MWH2O is also defined as MH2. This is also defined as MH2O.